Hello everyone, good evening. Dear authors and invited guests, welcome to technical session 6C. Myself, Vidhi Rahangdale, and this session would be moderated by me. On behalf of Global Knowledge Research Foundation and GR Scholastic, it is my great pleasure to welcome you to the 11th International Congress on Information and Communication Technology, that is ICICT 2026, London, UK. The 11th edition of the conference is being organized in a hybrid mode. The physical event was held yesterday in London, UK, and the virtual event is being held through Zoom from 25th to 27th February 2026. I hope you will be enjoying the knowledgeable and interactive sessions throughout the day. In this session, we have 6 presentations. Each presenter will be given 12 minutes for the presentations and 3 minutes for question and answers. On 10 minutes, I will raise a gentle reminder. There is another request to all the participants that you all stay connected with us till the closing remarks. If you have any query or update, then you can write it to me in the chat box. Just before we start the session, I would like to introduce you to the chair members. We have Dr. Ali Tharir Hamid and Dr. Nalini Kant Joshi as our session chair. Dr. Ali T. Hamid is an associate professor in the College of Engineering at University of Diyala, Iraq. His research areas include swarm intelligence, control systems, and renewable energy systems, with active involvement in teaching and research in engineering. Then we have Dr. Nalini Kant Joshi. Dr. Nalini Kant Joshi is the director and professor at Modi Institute of Management and Technology, located Kota, India. He brings over 25 years of extensive experience in academia, research, and institutional administration, contributing significantly to higher education leadership and development. Now, I would like to welcome Dr. Ali Tharir Hamid to welcome us all to the session. So, your remarks?
Thank you so much. Thank you so much. Welcome to you. Thank you so much. You can start it?
Yes, sir. We will start with the presentations. We invite.
Right now, first of all, I want to explain about something about myself. My name is Ali, Associate Prof. Dr. Ali Thayer. I'm from University of Diyala of Iraq. Welcome to everyone in this session. Welcome to VD Radiangeld and Dr.
Yes,
Joshi. This is session chair. Thank you for Springer Nature to create this invitation and this conference. First of all, I want to know which one is arriving early. I think all of them is arrived, so we can start with session number 1 or article number 1 presented by Fahmi Jafar, analysis of hybrid deep learning method for cyber attack detection in Internet of Things. A reference comparative study. Is there here? Anyone here about this conference, about this article? Okay. Can you present it, please? Anyone here to present its conference, its article, to make a presentation? Can you go to next? VD, are you there?
Sorry, Felix Fernandez, I can do it.
Yep, you can do it. Go ahead.
Okay, thank you very much.
Yeah.
I share my presentation.
Yes.
Sorry, can you confirm if you are able to see the presentation, please?
Yep, it is working properly.
Perfect. Well, my name is Felix Fernandez. I'm a teacher, a professor at Universidad Técnica de Ambato in Ecuador, in South America. And it's a pleasure to meet all of you here in this session just to talk about this work, whose objective has been to enhance personal savings management systems with the use of conversational AI. Well, actually, we're in a project, in a research project for measuring the actual impact of generative AI right now in the building of different applications. And in this case, this talk is about an application that some students of mine actually built in only 24 hours in a Concord ship a few months ago, in which the goal was to build some application, not necessarily with AI, in order to help people to save money. It was something like that. And what it was found in this area was that personal finance management systems are actually under-supported by AI-driven solutions, and that conversational AI has mainly focused on investments and not on this issue of saving goals that people might have. So it was interesting that these students of mine actually focused on this specific target, trying to build this application with conversational AI supporting the management of data for personal savings. As current limitations, we found when we look at the literature that existing tools focus on tracking actions as management systems, but they do not focus on behavioral support of the users. Conversational agents often lack contextual integration with user financial data, and it is, of course, or in our opinion, also as far as I'm concerned, due to ethical management of AI and the trustability that we might have on its behavior. And of course, the usability of these kind of applications is something really that really matters in order to get a factual adoption in financial applications. So in this slide, I'm presenting some of the applications that we actually look at when we try to identify some that could be doing something like what we actually got with this application of my students. And the thing is, as I previously said, that it is really hard to find an application that is making use currently of AI, generative AI, in order to support the behavior of the users of this kind of application. The way that the application was built was using an agile development methodology, Kanban in this case. I have to mention that it was 3 students were involved in the creation of the application, the implementation of this application. As I previously said, as I previously mentioned, they had only 24 hours to build the application. And these students actually used an architecture, a multi-layer architecture, using programming in JavaScript, specifically using TypeScript. And for measuring the results, we applied the system usability scale for 20 participants, 20 persons involved in the research, in order to identify the actual impact of the application that was developed. In this slide, I'm presenting the characteristics of the participants in the research. As you can see, it's a small sample size. Only 20 persons were involved. The age range from 20 to 45 years old people. Participants were male and females with quite an experience in ICT. I have to mention that only 45% of them had previous experience using saving apps. Here, I'm presenting the architecture, the overall architecture of the application. As I previously mentioned, is divided into 3 layers. As you can see here, the front-end layer implemented using Next. In the backend layer, we have the components or the modules for interacting with the generative AI. Here, the Open Router was used just to get into the interaction with the ChatGPT, actually in this case, or OpenAI model to get the results from generative AI. The management system of the information is represented here in this model, and it was also used a model for exchanging mails to the users. And of course, there's a model for authentication of the users in the application. A Postgres database was the chosen database to be used. In this slide, I want to focus on the characteristic for exchanging information with the API. As we can see here, programming is actually changing when we use this kind of technology, because in this part here, we create a pre-context, a preamble of the communication between the backend of the application with the conversational AI, and we are specifying the role that the AI is going to accomplish in this kind of exchange. The one thing that we actually find that this solution contributes is that the goals of the users are actually included in the communication, which provides a more deeply and consistent feedback from the AI in order to improve the behavior of the user using the application and get into the goals that it's actually what matters for the user. This last part here is just the request that is made to the API of the conversational AI in order to get the result. In this other slide, we're seeing how we're configuring or specifying the data to be used by the AI in order to get a result, but specifically for one goal. In the previous slide, all the goals are sent to all the goals that the user have as saving goals are sent to the AI. In this other occasion, only one specific goal is being sent to the AI. The result in terms of the user interface is what we see here. On the left, we have just a conversation between the AI and the user, just giving the user some feedback and some suggestions of what to do in order to save money. And in the right, we see what the AI suggests for getting a specific goal done. So in this case, it's a travel to Japan. We have some specific savings and some time to get the whole saving achieved. And well, there's an interaction in which the AI is just telling the user what to do in order to get it right. In this slide, I'm showing the notification that the user got through email, and this is important because the solution is not based only on AI, as we see here, but in other technologies that make easier for the users to use the application. So this is the case of this email exchange format that we see here in order to notify the user how the things are going on. And as you can see here, some dashboard that also helps the user to identify its position, sorry, in order to get the goals. As a whole, we got these results applying the usability scale that actually we could measure by applying this sort of survey. And as you see, we got a final score of 78.1, which is a good score. And it means that the usability is considered high, in this case, for this kind of application by the users that participated, that actually participated in the study. This is the case of one of the positive questions is how intuitive and easy to use is the application, is considered the application. And most of the users, potential users, consider it high level of intuitivity and easiness of use. And this is one of the questions in the survey that were less approved by the users, actually. As you can see here, it's only 4 or 5. All the others are have higher scores. And in this chart is presented how unnecessarily complex is the application. The application is considered quite simple and quite easy to use by all the users, and this is quite a significant result as far as the evaluation is now. So in summary, we found out that the overall SUSE score was 78 in this case. It's a good level of usability. Users highlighted ease of use and learnability of the application, and potential users emphasized the existing synergy between the AI, the dashboards, and email notifications. It's not only about using AI, but integrating AI with other functionalities that make the application usable. As conclusions of our work, we see that integrating conversational artificial intelligence with interactive dashboard and a proactive generation of reminders actually constitutes a viable strategy to promote personal financial discipline. The results obtained reflected a usability level rated as good and close to excellent, and the ease of learning and coherent model integration and low perceived complexity were highlighted by potential users, which is a good result. As future work, we see that it is important to carry out further evaluation of the results with bigger sample size. There were only 20 participants in this quite a small research. To include participants without experience in the use of digital tools. That's something important in order to expand the sample number, and to ensure stronger guarantees of privacy by using local deployed LLMs. And this is really important because, as you could see, for this prototype of the application, an open LLM was used, but it was used in an infrastructure that is external to our facilities. And of course, for the financial environment, sharing information about the users is not a good idea. I'm sure we all will not agree on that. So using the LLM in a local facility is really important in order to deploy this kind of infrastructure, if this is the case. So it has been my presentation of our work. If you have any question, all yours. Thank you very much.
Thank you very much, Felix Fernandez from South America. Your present was very easy and clear. Thank you so much. Any question, please?
So, Felix, your presentation is very good enough, very easily understood. And of course, this topic is relevant and it has a very good future scope. Thank you.
Thank you very much for your comment.
Please, every participant, please, you should make a presentation in 15 minutes only, please. So anyone else can make a presentation?
Okay, thank you so much. Maybe I can
Thank you.
present.
Thank you.
We now invite Elliot Munges to present their paper titled Comparative Analysis of Deep Learning Models and Explainable Artificial Intelligence Techniques in Detecting Tuberculosis Among HIV-Positive Patients.
Okay, thank you so much. I've sent a request to be allowed to share my screen.
Okay.
Okay, thank you so much, Chair, for giving us the opportunity to present our work. Kindly confirm if my screen is visible from your end.
Yes,
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 it
it is
is.
visible.
It is visible.
Yeah, go ahead, please.
Okay, thank you so much. Also, I'd like to take you through our research work centered on comparative analysis of deep learning models and explainable AI techniques for tuberculosis detection among people living with HIV. So this work was done by 3 scholars. Number 1 is Mr. Bright Mugigo, myself, Elliot Mbunge, and then Dr. Button. So, right, what motivated us to do this particular study is that we have a significant number of population among people who are living with HIV that are severely affected by tuberculosis. And here we are talking about active tuberculosis. And as we know that tuberculosis is actually a preventable and also a curable disease, but we are constantly recording high significant numbers of casualties affected by TB, and especially among people who are living with HIV. So as for 2023, these statistics, we took it from the World Health Organization. We have a total of 1.2 million TB-related mortalities that were recorded in that particular year. And among these, some of them were related to HIV and TB. So it's actually a significant number if we look at the statistics. So we're actually having a big problem, because if we look at 261,000 mortalities that are related to HIV and TB. So this actually motivated our study. So as we know, we have the conventional methods or the traditional methods that are used to diagnose, like the sputum test or the gene expect. But in some many low and income countries, we have a significant shortage in terms of resources that can be used to test, especially using the sputum test and the gene expect. So, right, then number 2, we also have another big challenge of manually interpreting the results from gene expect and sputum tests. So these are some of the reasons that motivated us to conduct this particular study. And again, we also realized based on the literature, we have a significant number of mortalities that are associated with delayed TB diagnosis. So, because of so many reasons that I've indicated earlier on, the lack of resources and the lack of experts that could probably manually interpret the findings. So based on this, again, like I said, in many developing countries, some of these tests that are conventional, they are not readily available. So we are trying by all means to come up with something that could benefit, and then make some early recommendations to visit the facility for further testing. So we've noticed a significant progress so far that has been made by different computational techniques and artificial intelligence techniques, including deep learning, especially the convolutional neural networks. They've been significantly used to detect TB in different settings. But we also noticed another daunting task, which details the actual implementation of these models in real life situation. And some of the reasons that were also highlighted by different scholars is the black box nature of these models, which then now affect their actual implementation or adoption in real clinical settings. So compounded by all these challenges, we then realized that there's a need to come up with an instrument that could be used by using X-ray images. Then we develop a lightweight TB detection that could be used in resource-constrained areas. But here, we are mostly focusing on people living with HIV. So this is the motivation. So going further, I just want to take you through the aims and the objectives. So number one, we already have some existing tools that are there, but like I indicated, some of them, they are not easily accessible in some areas. So we want to come up with something that could be used to detect TB and then make some recommendation for further testing. But again, we're trying to infuse the explainable AI models to improve the interpretability so that it will also tackle the issue of black box nature of models. So we applied 3 convolutional neural network models, and these are deep learning models for our simulation and also for our experiments. And we use the chest X-ray images that were collected from people living with HIV. These are HIV positive patients. And then after that, we then compared the performance of these models based on sensitivity, specificity, and also we looked at accuracy and then the area under curve to see the training loss and the performance of the model. And then after that, we then identified the most suitable model. Here, we just looked at the best performing model specifically on sensitivity, which is the recall, the ability of the model to detect positive cases. So we then collected our data, and after that, we also looked at different work that we conducted prior our research. So we noticed that there are quite significant of them, but we selected a few of them that aligns with some of the models that we implemented. So we have different scholars like Raju. They also implemented some CNN-based models. And we also have the HEO also implemented the CNN. And these models, they actually recorded promising results in terms of sensitivity, accuracy, etc. So having done our comprehensive literature analysis, we then selected the best performing models, and those are the ones we did the experiment on. So to effectively implement our experiments, we collected data from Beatrice Infectious Disease Hospital, and this is a disease that screens HIV patients and also tuberculosis in Harare in Zimbabwe, which is a country that is located in the southern part of Africa. And then we collected data, and here we are referring to X-ray images from January 2024 up to April 2025. And our data set consisted of 1,400 anonymized chest X-ray images. And among these, we have the 500 positive. These ones, they tested positive, especially on TB. And then we have 900, the negative. As you can see, when we did our implementation, we noticed that there was a class imbalance. So we implemented some data pre-processing techniques to address that. And then before collecting data and doing the implementation, we applied for ethical clearance from the university, from Chinhoyi University of Technology, because this study was conducted at Chinhoyi University, though we collaborated with some other institutions, but the ethical clearance to have access to such highly classified data, we got it from Chinhoyi University, and then we also got the approval from the Beatrice Infectious Disease Hospital. And then after that, we applied our 4 models, VGG16, and this is a convolutional neural network model, like I've said. The choice or the reason for selecting this was informed by the literature. As we know, the VGG16 is a simple architecture, but from literature, it also performed well in terms of sensitivity. So it recorded high sensitivity in different studies. And then we also used the Inception V3. This is a parallel convolutional filters with efficient computational strength. So we also implemented this. And then we also implemented the DenseNet 121, and with this one has got the dense connection. And we also have another strength in terms of improved feature reuse. And also we have, the reason also we selected this is because it has got reduced vanishing gradient problems. So we selected this because of that. And then we also selected the MobileNet version 2, which is a lightweight deep learning model. And this one can operate in low resource and mobile platforms, which is also good for deployment. And then after that, for explainability, we then implemented two methods, the GradCam and then the LIME. And after that, we then assess the performance of these models based on accuracy, specificity, sensitivity, and AUC, as I also indicated earlier on. So after doing the implementation, our pre-processing and so forth, annotation, we also applied some SMOT to also look at the images, the annotation, and we also did the pre-processing. So these are the results that we captured after implementing those data pre-processing techniques, like I indicated, the resizing, the grayscale concentration normalization using Minimax, and also the data augmentation. So then we implemented the models, and we recorded their performance based on those four standard key performance evaluation metrics. So in our implementation, we noticed that our DenseNet actually performed well in terms of sensitivity, and also in terms of specificity, and also accuracy. So we also noted that our MobileNet V2 also performed very well in terms of those performance evaluation and metrics that we implemented. So we then also checked to see the performance of these models during the implementation, looking at the receiver operating system operating curve, and here talking about the AUC curve, to look at the actual performance true positive rate versus false positive rate. And we also recorded, and then in all this, we noticed that again, our DenseNet actually performed well and recorded the high AUC value. So these are just the graphs that we extracted for each model to say how the model performed as we were progressing. And then in terms of explainability, we then, like I said, we implemented the GradCam and then the LIME to see the regions that influence the model's prediction. So for each particular image, we just selected a few. We couldn't select all of them to say how the interpretations were made for display purpose and also for demonstration purposes. So we noticed that yes, these two explainable AI techniques, they were able to give us some explanations on the regions that significantly influenced the model's prediction. So for our DenseNet, we have the GradCam, right? And then the LIME images there. GradCam is the one on the middle, and then the LIME is the one on the far right, and it shows the regions that were used to determine or to detect TB from those checks, the X-ray images. And then this is just a continuation to illustrate, but again, on different positions or origins of the images to show the regions that will also influence the model's predicted outcomes, and the regions that also influence how the model arrives to say this is actually a TB positive and the TB negative. So in conclusion, we realized that yes, deep learning models, especially the explainable ones, they actually play an important role in if they are implemented properly based on the clinical guidelines and regulations following all the policies in place, they can significantly improve or enhance the TB screening, especially among the people living with HIV and people living in resource-constrained areas. And from our implementation, we also noticed that, yes, among those best models, the DenseNet specifically for this particular data set actually performed very well as compared to others in terms of the performance evaluation criteria that we used to assess. And then actually, we also noticed that the combination of these CNN-based, especially for this particular study, DenseNet 121 and the explainable AI, they also provide very good, meaningful explanations. If we look at the images that were used to determine the regions that influence the model's predictions, we notice that it's a very good combination. If we could adopt this, I think we might increase the adoption rate or build trust on our so-called black box models. And then in terms of the implications, like I've said that, yes, we have TB among HIV as a public health concern. But in some instances, we are using the conventional method, the sputum, and also the other methods. But some of these ones, they are not easily accessible, like the gene expect in some areas. So if we're to improve this prototype and take it further, package it and deploy it as an experiment in some resource-constrained area, it might be cost-effective too for early TB detection and also make some recommendations. And when we do that, we also contribute something meaningful to the community. And we also notice that this is one of the goals that are also being pushed by the regulator, the health organization, to eliminate TB. So we are trying to contribute something meaningful in those strategic plans to eliminate TB. So these are the references that I've used for this particular presentation, but in our article we have more. So this is the end of our presentation. Thank you so much, Chair, for your time, and thank you so much, colleagues, for dedicating your time and listening to our presentation. Thank you.
I
Thank
request the
you.
chair to ask questions.
Thank you, Mr. Aloyitz. Thank you for your presentation. Any question, please?
So, highlight your presentation is good enough, and you have uses four deep learning models. So, of course, it's a good enough, but a very simple one question from my side, that you have selected four deep learning models. So, is there any specific justification of using these four models, or you could have selected some other models?
Yeah, thank you so much for the question. It's a very good question. So, what informed us to select these models? Number one, right? We did our comprehensive literature analysis, and we noticed that these four, all right, they performed very well. And then we include the mobile net version 2 in terms of the deployment platform, because this one can work very well on mobile platforms since it's a lightweight deploying model as compared to others. So that actually informed us to select these four. So those three, they're actually high computation in terms of resources, but again, they performed well based on the literature that we analyzed, because some of these models that were also implemented to detect TB by different scholars. So we selected those, and also MobileNet among those other studies, it was also included. But again, we further selected it because it's a lightweight model. It can work very well on mobile devices. Thank you. I don't know if I've answered you.
Okay. It's fair enough. Thank you.
Good. Thank you.
Next presentation, please.
I would like to invite Mehde Daryanwad to present a paper titled Do Scenes Matter? Analyzing Scene-Aware Attribute Learning for Image Aesthetics.
Can you see my presentation?
Yes, we can.
Good evening, everyone. Thank you for joining my presentation. My name is Maida Daryanavad. I'm a researcher in Faculty of Science and Engineering at University of Groningen in the Netherlands. This is a joint work conducted with my team, and today I will present the result titled Do Scenes Matter? Analyzing Scene-Aware Attribute Learning for Image Aesthetics. We work on computational aesthetic or beauty, a subcategory of image processing and deep learning-based image aesthetic quality assessment. I will start the presentation with a basic concept, aesthetic feature and related application. Then I will introduce the dataset used in our study, followed by the purpose approach and analysis. Finally, end with the conclusion and future work. First, let me explain the definition of aesthetics. Based on Oxford Dictionary, beauty is a combination of qualities that please the sense, especially sight. Based on this definition, it raises the question of how an image is perceived as beauty or beautiful, and how its aesthetic quality may be evaluated or scored. In many cases, evaluating image beauty is not straightforward. This is because aesthetics perception is influenced by environmental factors such as culture, history, and religion, which shape individual preferences individually. These factors highlight the complexity of aesthetics. Since the human judgment is often biased by these factors, researchers have adopted computational models, image aesthetic quality assessment or IAQA, to provide more objective measure of image aesthetic. For measuring the image aesthetic or in IAQA, some photographic rules are considered by critics to measure aesthetic. We call these rules aesthetic attributes. Now I want to briefly explain these attributes. Aesthetic attributes play an important role in capturing aesthetic of image, such as the rule of third, depth of field, balancing element, and so on. For example, the rule of third places the subject along with imaginary grid lines and PowerPoint instead of the center to make the image more balanced and interesting. You can see the image with and without the rule of third. Depth of field refers to how much of the image is in the focus. A shallow depth of field blur the background to highlight the subject. As you can see, the image with and without DOF here. And balancing element means that arranging the image balance and object to a feels stable and pleasing. This can be a symmetrical balance, asymmetrical balance, or color balance. And image aesthetic quality assessment have been used in various applications. For example, automatic image generation, fashion, and so on. And you can see here the automatic image generation and fashion. It can suggest you as a pleasing image for pleasing harmony for your clothes or something like this. And the product design, as we can see here, when you're presenting a product, you try to make it as appealing as possible. And the image recommendation, for example, when you search for an image on Google, you don't want to see an image with a poor aesthetic quality. And also, the image aesthetic quality assessment or IAQA can use in image enhancement. With the emergence of deep learning, several studies have been conducted on image aesthetic quality assessment using deep learning methods to capture the complex subjective nature of the aesthetics. However, most of the deep learning based IAQA methods treat the aesthetic attribute independently without considering the scene content or image categories. In fact, the interpretation of aesthetics attribute are highly content dependent, shaped by the genre of image and the creator intention. It motivates us to analyze the relationship between the photography scenes and aesthetic attributes. We conduct a systematic scene-wise analysis of the aesthetic attribute using a data set with both scene and attribute annotation. We show them that the aesthetic quality assessment is strongly scene dependent, and we show that the importance of the aesthetic attributes varies significantly across different scenes. And also, we provide the structural interpretation of scene based on the attribute score relationship. Actually, we use the Composition Assessment Database, or CADB, which has both scene and attribute annotation. This database has almost 10,000 RGB images sourced from Flickr website, and all images are real, which means does not include non-photographic images such as edited image or cartoon image or something like this. And each image has an overall score and 11 attribute score. As you can see here, these are low and high aesthetic image from animal scene. And attributes include the score of the balancing element, color harmony, content, DOF or depth of field, light, motion blur, and so on. This database has 10 different scenes from animal, as you can see here, architecture, human, to aesthetic. You can see the random sample of each scenes here. For the purpose approach, actually, to understand the data before applying the statistical test, we illustrated the distribution of the aesthetic score for each scenes. You can see the violin pilots show the clear difference among scenes category. The scenes such as a plant and animal show a higher median score, indicating that the image in these categories tend to be rated more. In contrast, the categories like others show the lower median and more skewed score distribution, offering the lower aesthetic judgment. In the next step, we use mutual information to visual the dependency between each attribute and overall score, allowing us to identify the attribute most strongly associated with aesthetic judgment. The top three attributes with the highest mutual information are content, light, and color harmony, as you can see here. To understand how these attributes score relationship vary across the scene, we investigate the mutual information analysis separately within each scene. A sample of the person analysis show that a certain attribute gain or lose importance depending on scene. Content is the most important attribute in all scenes. But about differences, for example, depth of field rank among the top three attributes with the highest mutual information in animal and plant scene, but become one of the lowest in architecture, falling below the rule of thirds, symmetry, and repetition. This indicates that the attribute importance is scene dependent. To investigate this similar dependency between aesthetic attributes and overall score, we construct a dendrogram for each scene. The dependency were quantified based on a pairwise similarity. Even though the scene in a group have a different visual content, they share the common aesthetic dependency. For example, here, animal and plant categories cluster together, indicating the strong similarity based on the aesthetic dependency pattern. To share the scene level attributes pattern, per scene Z score were computed to present how many standard deviation and attribute value is above or below their overall mean of that attribute. For instance, the night scene showed strong responses for light, indicating that, as you can see here, sorry. as you can see here. The light indicating that the illumination is a key factor influencing the aesthetic under low light condition. And for example, for the landscape and plant, you can see the color harmony is important. It means that the color important in these categories. And in conclusion, this study investigated the role of scene information in the image aesthetic quality assessment. We found consistent evidence that the aesthetic assessment is strongly scene dependent, and different image category have a different aesthetic patterns. And for a future work, actually, could involve the detailed analysis of scene evaluation for the impact of the image or evaluating scene category and development of appropriate pipeline for similar sense, for example, or the enhance the model robustness and generalization. Thank you for your attention.
I request the session chair to ask question and answers.
So it is well presented, and one of the key factors, I would say, scene attributes.
Yeah.
That is very important, and you covered scene attributes, and I can say that the scope of a future in your work is purely move around the scene attributes. The more depth inclusion and analysis and more work will give a good result in future by considering the attributes. And it is a vast involvement of attributes and parameters. So of course, it's in a starting point, but huge scope do exist. Thank you.
Thank you. Thank you.
Thank you for your well present.
Yeah.
Have you good luck.
Thank you.
And please, we want to start with the new present, please.
Thank you.
Thank you. We will now invite Felix Fernandez Pena for his presentation on paper title Enhancing Personal Saving Management Systems with the Use of Conversational AI.
Sorry, but I already presented my paper.
Yes, right. He's the first one. Right. Go to next, please.
Yes, sir.
Good evening. Can you hear me? Hello?
Yes, you
Yeah.
properly. That's right. Go to next. Yeah.
Oh,
Go
thank
ahead,
you so
please.
much.
Go. Yeah.
Thank you so much. Good evening, everyone. My name is Christivi Kalambai, and today I'll be presenting our work, which is titled "Integrating Explainable AI with Smart and Synthetic Data Augmentation for Improving Tuberculosis Prediction Among Adolescent and Young People." This work was conducted in collaboration with Dr. Shopi Dube and Prof. Elliot Bunge. Tuberculosis remains one of the major health issues worldwide. In 2024, the World Health Organization recorded 10.7 million of cases and over 1.2 million of deaths globally. Adolescent and young people, they are particularly at risk because they often experience delay in diagnostics, and also they are vulnerable to social exposure. Therefore, machine learning has shown great promises, but is still struggling with issues that lack class imbalance, where TB positive cases are fewer than TB negative cases. Overfitting, which usually happens in smaller data set, and the lack of interpretability, which it limits clinical trust. Therefore, there is a need of an accurate, robust, and explainable TB predictive model. Previous studies have shown the usefulness of machine learning in tuberculosis prediction, such as the random forest support vector machines and decision tree, which has shown strong predictive models performing outcomes in their study. The machine learning, which has improved the outcome prediction in pulmonary TB, and also most recently, explainable AI has been emphasized as very important for clinical adoption. However, the gaps that are still there is that most studies do not focus on adolescent and young people. Most studies do not address systematically the class imbalance issue, and there is a lack of an integrated class balancing, synthetic augmentation, and sharp into one integrated framework. Therefore, our study contributes by combining SMOT, synthetic augmentation, to improve and also SHAP to improve the prediction of tuberculosis. The research objectives are improving the tuberculosis prediction among adolescent and young people, addressing class imbalance using SMOT, applying synthetic data augmentation and enhanced generalization, and integrating explainable AI and to enhance to enhance interpretability, and also to validate the risk factors. So we used the data set from the trade TB infection baseline data set, which comprehended of 2,552 participants aged from 15 years old to 24 years old from Zambia. The target variable was binary, so we had the TB positive and the TB negatives. Pre-processing included the mode imputation for missing values and one hot encoding for categorical variables, and then the stratified strain and test split. Now, to address the class imbalance issue, we applied SMOT, but this was done only to training data to to prevent data leakage. Then now, to further reduce overfitting and improve generalization, we used synthetic augmentation techniques like bootstrapping, the Gaussian noise injection, the Koleski decomposition to preserve the correlation structure. Then now the final data set resulted into 50,000 balanced samples, and we tried to preserve the statistical properties. Therefore, it was confirmed using the Kolmogorov-Smirnov test. The model used in this work was the multi-layer perceptron, the random forest, and the gradient boosting. And we evaluated the performance of this model using our evaluation matrix, which were the accuracy, precision, recall, F1 score, and the O-CROC. But now, given the clinical context of our study, we prioritized the recall and the O-CROC. Now, our results. So before augmentation, we can see that our models performed reasonable. with MLP, which was the best performing model here with an OC of 0.5. Sorry?
Excuse me, ma'am. Sorry for interrupting, but your slide is not indifferent. We are able to see only the first slide. That
Excuse
too
me?
in. We are not able to see your slides. I'm sorry to interrupt, but
Oh, I'm so
only we are
sorry.
able to see only the first slide.
Only the first.
Yes.
I'm sorry.
So
Can I try sharing
You
again?
can use edit from from upstairs. Edit. You can press
Sorry.
edit. Press edit, please.
Sorry. Okay. Can I try to reshare again? Is it much better now? Can you see something?
You can see
we are able
enable
to.
edit. Enable
Yes,
edit.
sir.
Sorry?
Yellow
You're
ribbon
carrying the
in our yellow.
Yes, enable editing on the top. Press on it, please. Enable editing. Enable editing and the yellow. On the upstairs. On the upstairs. You can see it. Enable editing.
No, I
You are
cannot.
close. Look.
No, press enable editing.
Hi, Christy.
More,
Just to move,
more high, more high, more upstairs.
move up where your mouse cursor is.
Oh, is it fine now?
Not yet. Just to move your cursor up a bit. Don't rush. Just go up. Up
Okay.
again.
More.
Yes,
Oh,
up
okay,
again.
okay.
Just
Sorry.
enable edit. Yeah, good.
It was on the
Yes, good.
presentation. I'm so sorry.
Good. Thanks.
I'm
Good.
so sorry.
But you're
Should I
presenting very
restart?
Share
Sorry, should I
again.
restart or I can carry on?
Yes, you
Share
can.
again your
You can share it
slides
again.
first.
Can share it again, please?
Sorry, did I stop sharing? Okay, let me share again.
Yes, now it's
Okay.
working properly. Yes, right.
Okay, I was asking if I should carry on or restart. Sorry?
On slideshow. Change it to slideshow.
Yes, right.
Okay. Should I restart or should I carry on with the presentation?
Carry on, please. Carry on. Yes,
Okay,
carry on.
okay.
Carry on.
My apologies. Okay, yes. So I was on the result. Now, before the augmentation, we can see that the results were reasonable, but they were not perfect because the model still struggled with minority class detection. And the best performing model here was the MLP with an OC of 0.57 and a recall of 0.532. And after applying SMOT and synthetic augmentation, we can see that the performance has greatly improved with the random forest as the best performing model with an OC of 0.963 and a recall of 0.908, which has shown that synthetic augmentation has significantly improved, reduced the overfitting, and improved the generalization performance. So now, to ensure that our results interpretable, we applied SHAP on our best performing models, and the top predictors were age group, alcohol use, household contacts, sex, and smoking, which also align with known epidemiological risk factors. Therefore, reinforces the clinical validity of our model. And also, it removes the black box nature of AI into interpretable decision support tool. Our contribution includes combining SMOT and synthetic augmentation in an improving the robustness of tuberculosis dataset, and and integrating explainable AI with and integrating explainable AI for a transparent risk prediction. Our limitation includes we did not use the model. I mean, we only used structured demographic data. There was no laboratory markers such as the gene expert, and the validation was only done internally. Therefore, our future work it would involve creating a multimodal clinical data and also external validation. So, in conclusion, combining SMOT and synthetic augmentation has significantly improved the performance of our predictive models. The random forest achieved the best was the best model performing model with a strong discrimination of an oak of 0.963 and a recall of 0.908, and sharp ensured transparency and also interpretability, the valid and interpretability of our models. And in summary, explainable AI can support early TB risk identification among adolescent and young people in high burden settings. Thank you so much.
I request the session chairs to ask questions.
It's a good paper and well presented.
Thank you so much. Thank you.
Your work is good enough.
Thank you for your clear present. Thank you.
Thank you.
Any question for this present, please? Okay, go to next, please.
Yes, sir. Now I would like to invite Sindhuja Panchala to present a paper titled Learning in Focus, Detecting Behavioral and Collaborative Engagement Using Vision Transformers.
Sure. Let me share the screen. Are you able to see my screen?
Your screen is visible.
Okay. It's the PPT. Excuse me. Hello.
Yes, it
Your
is working.
PPT
Yes.
is not.
Just PPT is not working. Yes. Just go to PPT
Okay. I'm sharing my PPT. Can you see this?
no.
No. Oh,
Yes.
just a minute.
Just open it. Just open it. Your full screen
I
is
open.
okay. Just open. No, it is not working. I think just make it minimize for Zoom. Make it minimize.
Okay.
Present.
Okay. Sure. Are you able to screen?
No, it is not working properly.
You shared the window, I think,
Okay.
wrongly.
And right,
I
Yes,
think
it
you
is
can
now.
see now.
Yes, it is working
Okay.
properly now.
Okay, just sure. Thank you so much for confirming.
Okay.
And just present.
Go ahead, please. Go ahead.
Oh, yeah, sure. Good evening, good afternoon, good afternoon, everyone. Uh, Firstly, welcome to 11th International Congress on Information and Communication Technology held in London. And thank you so much for this opportunity. And today I'm going to discuss our paper titled Learning in Focus, Detecting Behavior and Collaborative Engagement Using Vision Transformers. So this is the author list, and I'm Sindhuja Penchala, from a graduate student from Department of Computer Science from University of Alabama, United States of America. And today I'm going to discuss the contents, the introduction, what mainly about the paper, the objectives of the paper, methodology, results, and the conclusion. So coming to introduction, Nowadays, it's very important for us to monitor children's engagement, like the cognitive development, the learning things, are they learning or not? So it's important for to detect the engagement, collaboration things in children, and if they have a lack of attention or interaction, it can affect negative. There might be some negative effects in the learning outcomes as well. And we have to focus mainly like, are the children, how attentive they are, like are they focused in the class, are they listening to the teacher or not? So all these are monitored in order to uh, need to be monitored because for the development of the children's future. So identifying these engagement levels manually is also a difficult thing right now. So in order to overcome this thing, we are going to use the automated methods to monitor the children's learning and behavior. So these are the main research questions behind this paper. First question is like, can we use the pre-trained vision transformers to detect the behavior and collaborative engagement? So how effectively are these transformer models can capture the gaze and interaction patterns, and which pre-trained transformer model performs the best for engagement detection, and can transformer models enable the automated and scalable engagement analysis? So in order to answer all these queries, we have come up with a solution. Uh, Earlier, we have used like convolutional neural networks. Those neural networks struggle to capture the long range dependencies. So they used to have a limited accuracy, and most of them have been rely on the handcrafted features. There are some limitations using CNN, and they did not perform well in the real world classrooms also. So there was some issue with the CNNs, and they were unable to capture the both local and global visual features. In order to overcome this, we have come up with a solution. Like we have used multiple pre-trained transformer models to automatically detect the behavior and collaborative engagement using the visual data of the children. So for this, we have curated and refined the child play gaze dataset with the improved lab. And we have labeled the dataset, use those dataset to detect the engagement levels. And here, out of all of the transformer models, we have used Sweet, and this perform better to capture the local and both local and global engagement features. Coming to data preparations. So in order to start with this, we need a data set. So here with the data set we used is the child case data set. It is one of the open repository. They have uploaded all the videos. First, we have downloaded all the videos of the child case. So those videos include adult and the child. Adult and child collaborations like in the classroom videos, rehab centers. So there are multiple places, public places, and the videos are downloaded, videos are extracted into frames, and those frames are taken, and those adult and child faces have been cropped. Those have been labeled accordingly. Uh, the main classes are collaborative, non-collaborative, engagement, non-engaged. So these are the main four classes that we have used, and we have split the data set into testing, training, and validation. So 70% is for training, 20 for testing, and 10 for validation. The models we have used is VIT, SIN, DEIT, VIT GASE, AP, VIT GASE TR. Here mainly we have focusing on the transformer models because we have earlier we have struggled with the CNS, so we did not choose CNS. We used transform models, and we also trained VIT gaze. So mainly this data set is about the gaze related. That's the reason we have used gaze related models like VIT gaze, VEIT, all these are the related transformer models. So if you see here, this table indicates the engagement. So let me do this. If you see here, you can see in the right column the child and the adult. Here, first class is the engagement. The child is looking at the adult, but they are not doing any task. So they are attentively listening to the adult, but they are not doing any task. This comes under engaged. And coming to non-engaged, it means the child is distracted, not doing any task, not listening to the child, adult, not listening to the teacher, and they're looking at somewhere else. And collaborative means child is actively engaged with the teacher and actively playing, actively collaborating. And coming to non-collaborative, they are listening to the teacher. They're not listening to the teacher, but doing some task. If teacher is telling paint, but the child is doing some something else, so he is not listening to the teacher, but he is doing something else. So in this way we have classified our data set. Like taking that data set, we have improved their data set and classified accordingly. These are the labels we have given. And next, coming to the methodology, as we told, like out of 6 models used, Swin has performed better. So this is the architecture diagram of the Swin. If you see here, let me. The input is given as an image. Here for the visibility, like we have used RGB image, but in order to have some confidentiality, we have used the CANI detected images. Like we have used CANI H to for the to for the privacy issues, we have used just CANI H images, but actually we used RGB image. Here the image is split into the 4x4 patch, and here next the patch partition is happening in the Swin transformer. Each image is divided into some patches, and each patch is responsible for the output. Like if you think there's a full RGB image, it is divided into 4x4 in the patch partition. Means like 224 is split into 56 by 56 56. So in the next stage, all those patches goes to like linear embedding. It means like a system doesn't understand the image, so it need to be converted to numerical data. So linear embedding is basically converting the image data to numerical data. Next, all this data goes through 4 stages. Like in SwinB, we have mainly 4 stages: 1, 2, 3, 4, and all the stages include layer normalization and window MSA, shifted window MSA, and linear MLP feed forward neural network. Then here, as we use, like there are totally 4 types of Swin transformers. Out of 4, we use Swin B, like Swin base. And with the depth of first stage includes depth of 2, second also depth of 2, 8 is the depth of 80, and fourth has depth of. In second, third, fourth, we have patch merging. So basically, in Swin transformer, what's happened is we have a patch merging task. Like here, if you see, it is split into 4x4, and each layer, if you go move forward, the patches are merged accordingly. So at last we will get a final output, and this is classified as a like as we classify, like we here we have collaborative, non-collaborative, engaged, not. So once the patch matching is done, we can have the classification. So coming to shifted window approach, this is one of the main important feature of Swin transformers. What happening here is like each patch is having like a shifted, like it is shifting to the other window, so that attention is not performing within the image, the attention is performing each window, so that we can have more important features from all the windows. It could give the better results. This is how Swin transformer works. Next, coming to these stages, here we use Swin B. This is the 4-stage hierarchical design, and the attention mainly is the shifted window, as we told, and this captures the local and global. If you see here, the output size is going decrease, like 56 by 56 in the starting stage, and it's going to be decreased by 7 by 7, and the window size is same. And if you see here, the 2 by 2, 4 by 2, all these are the feature maps: 128, 256. Here, 1024, I'm sorry, 1024 is like in the stage 4, almost all the important features have been extracted. Like using these important features, we are going to classify whether the image, like whether it's attentive, like collaborative, non-collaborative, engaged, or non-engaged. So this is mainly about the SwinB transformer. Coming to data augmentation, if you see here, the number of classes of collaborative, non-collaborative, engaged and non-engaged are imbalanced. So there are most of the engaged classes. So we firstly earlier we have some overfitting issues. In order to overcome those, we need to have some like data augmentation techniques. So let me this. First, we applied fivefold cross validation, but it did not perform or achieve better results. Then, after we used oversampling to balance the minority classes of this non-collaborative and reduce the bias thing. But again, the fivefold did not work, so we applied the data augmentations techniques like cropping the image, adjusting the color, rotating the image, flipping, and all of those. Then it performed much better. Like instead of memorizing, the model is generalized well across all the engagement classes. Like it is able to tell the collaborative and non-collaborative, engaged and non-engagement classes. Next, coming to the results, see here, this is the confusion matrix of VIT confusion, VIT model. And this is about this Swin confusion matrix, confusion DEIT confusion matrix, APVIT gaze here. So as just to be more precise, we have used gaze detecting models and also transformer, like all the transformer models. If you see here, Swin confusion matrix, engaged, not engaged, collaborative, non-collaborative. So the diagonal, the number is like 564, 114. So almost in all classes, Swin has performed better compared to other models. And these are the ROC curves. And the first one is the VIT, second is for SWIN, third is for DEIT, GSTR, APVIT, and the so second one here the AUC of one for like engaged, not engaged, collaborative, not collaborative. So it's performed much better than remaining. Here we have precision, recall, F1 score, accuracy, and parameters. Almost all transformers performed well, but among six, Swin has achieved better in the person like 0.975. Even VIT, DEIT performed well, but just a minor. But Swin has performed better, like with 97% with the F1 score of 9701 and a recall of 9805. Coming to precision, like DIT have best precision among everyone, and these are the parameters. So DIT of 86 million parameters, VIT, DEIT has 86 same, and for VIT gives 22 million parameters. Like they have not included the parameters in the paper, so for that, and Swin has 88 million parameters. This is all about the results of the models we used. Conclusion. So finally, I just want to conclude like we have evaluated, like we have used six pre-trained transformer models using the child play gaze dataset, and among all the models, uh, they were able to detect the behavior and collaborative engagement. Out of all models, the Swin has performed very better, like best results with a 98% of my 97% of accuracy, and also it confirms that transformers are performing better, effective compared to convolution neural network in the engagement classification. And in future, we are also planning to focus on the video based detections like the streaming video. If you give a video, it has to classify the engaged, not engaged, collaborative, not engaged. So this is our future work, and this work is supported by the Brains Lab, Bio-Inspired Robotics, AI, Imaging, and Neurocognitive System Laboratory in the Department of Computer Science at University of Alabama. And I'm from Brains Lab. These are the references we have used. So I was unable to add all the references, but we have added the main references here. And any questions, please? Thank you so much for the opportunity.
I request the chair to ask questions.
So, Sindhuja, it's a very good
Yes,
presentation and very good work you have done, and it is well
thanks.
presented. So good work.
Thank
Thank
you.
you.
Thank you so
Thank
much.
you for your clear presentation. It is very well. Thank you.
Thank you. Thank you so much.
Any question, please? It's okay.
Hi all. I don't have a question, but my name is Femi Jafar. I'm from Quebec University at Chicoutimi, and I should present the first paper, but for time shift, I did a mistake regarding the time. Yeah, this is my paper.
I would like to invite Mehmi Jafar for presenting his paper titled Analysis of Hybrid Deep Learning Methods for Cyber Attack Detection in the Internet of Things, a reference comparative study.
Okay.
Go ahead, please.
Thank
Jafar.
you.
Go
Yeah,
ahead.
thank you. I will share my screen. Yeah. So can you see my screen?
Yes, we can see your screen.
Okay, great. Okay, so I'm from Quebec University at Chicoutimi. I did this study with my student, master student Jim Batty.
Please, Jafar, it is sharing your
Excuse me.
screen, PPT.
Yes.
Yes.
Just sharing your PPT, not your screen. Now it's appear your screen. Just share your PPT, please.
Okay, just 1 second. You can see my my PPT
Yes, it's
now.
now working properly. Yes, right.
Okay, great. Okay, so I did a study with my student Jim Batty. He's a master student, and the goal was to make a comparative study to compare the performance of deep learning method and classical method when we are detecting Internet of Things cyber attack. Why we are interested in this topic? Because we have a rapid expansion of IoT ecosystem. We have an increased attack surface with the connected environment, connected devices. With the IoT, we have heterogeneous and resource-constrained devices. So we need like to detect sophisticated multi-class cyber attacks and to know what are the best method to detect IoT cyber attack. So the main question here is to identify the performance of hybrid deep learning models and to compare the performance of these models with the classical machine learning models. In fact, in literature, we lack a unified comparison framework to make this comparison. And we have different data set processing pipelines. So it's difficult to reproduce the previous studies. So here we choose to work on 8 different class of cyber attacks, 8 different type of cyber attacks, and to make like an empirical comparison between machine learning and hybrid deep learning models when we are detecting this 8 type of cyber attacks. For the cyber attacks or for the cyber the 8 classes, we have the denial of service attack, the distributed denial of service attack, the scanning, the spoofing, bootnet, brute force, and web attack. We used this data set, CICIOT 2023, that is available through the website of CIC, the Canadian Institute of Cybersecurity. And it's publicly available, so we can reproduce the empirical study and reproduce the result of the study. The goal, the first step is to like set up the methodology. So get the data, making the data pre-processing, data cleaning, normalization. Then before starting the performance evaluation of different machine learning and deep learning methods, We make use standard scalar for feature scaling. We certified the under sampling to make class balancing. And we use the same pre-processing for all the evaluated models. Here, the evaluated models, we have logistic regression, random forest, and for hybrid deep learning, we have CNN. CNN composed with LSTM and stacked CNN LSTM. Here, the details of the empirical study configuration or setup. For the optimizer, we used Adam. For the learning rate, the batch size, the maximum epochs, the early stopping patience, the low function, and the hardware we used in our empirical study. For global performance of the evaluated model using the CIC dataset, we found that for accuracy and F1 score, random forest was the best model. In fact, with CNN, we have a strong detection of botnet and DDoS. If we go through the different cyber attacks, we found that the CNN had strong detection of botnet and distributed denial of service attack in IoT, but it made confusion between brute force and recognition attack. For CNN LSTM, we have an improved CNN when it's mixed with LSTM. We have an improved denial of service attack detection, but the distributed denial of service attack is often confused with the denial of service attack in the IT context. For random forest, we have like a stable performance across all classes. We have reduced false positives, and we have strong separation between attacks categories. So we can make the difference between the different categories. We didn't observe a confusion between the different categories of cyber attacks. Here we have the accuracy comparison, the ROC curve comparison for random forest, CNN, logistic regression, and CNN, then LSTM or stacked CNN LSTM. What we observe is that for the results, ensemble-based method remain highly competitive if we compare it with the classical method with the random forest. It's true that random forest is the best model, but ensemble-based method remain highly competitive. So as a conclusion, we found that classical ensemble method outperform hybrid deep learning models in IoT cyber attacks detection. We observed that an increased architectural complexity does not guarantee better performance when we are dealing with IoT cyber attacks detection. And we found that persistent confusion among behavioral similar attacks, mainly for the deep learning models. As future work, I would like to evaluate an additional data set regarding cyber attacks, including other kind of cyber attacks for IoT, like crypto jacking or fraud impression based on IoT. And we would like to combine ensemble learning with deep feature extraction. And we would like to integrate XAI, external AI methods to explain the performance of black box models like deep learning models. Thank you.
I request the session chair to ask questions.
Thank you, Mr. Jafar.
Thank you. So thank you. It's a good presentation. Well presented. Thank you.
Thank you. Thank you so much.
Any question, please? For all participants, any question, please? It's okay. Good luck.
So we will be moving on to the next part of the session. I sincerely thank our authors for their excellent presentations and contribution in this session, and all our participants for being a part of this international conference. I hope this session was informative enough. We, on behalf of the whole team, thank you for the support during this 11th version and all the previous 10 versions of the conference. We will be happy to have you in the 12th version in 2027. All the presenters would be getting their digital certificates through email within 2 working days. The publication will be live within 7 to 8 months. Kindly cooperate with the team of ICICT 2026. I also thank our session chair, Professor Ali Thari Hamid, and Professor Nalini Kant Joshi for chairing the session. A token of appreciation to the chair on behalf of the team ICICT 2026 and Global Knowledge Research Foundation and partners. Thank you for your valuable presence. I kindly request you all to switch on the camera for a quick snapshot of the virtual conference.
Thanks for the presentation and having the opportunity for the session chair. All in all, this session was very interesting.
Thank you, everyone. You can leave the meeting.
Thank
Have a
you.
good day.
Thank you for everyone. Thank you
Stay
for your
safe.
participants. Thank you for your speaker. Good luck to everyone.